Yesterday I mentioned that factoring is actually a big part of this unit. And what we'll use it for primarily is kind of what you could think of as simplifying stuff and looking at how to make, I mentioned yesterday we'll be adding and subtracting these rational functions, so that's how we'll find a common denominator. That's one way that we'll use it. But being able to find the zeros is there is some importance to that, but it's not as big of a deal as it was last unit where we were finding all those different zeros of the polynomials. So factoring and somewhat this will be two important, pretty darn important skills. When you see one like this, what's your first step? Like first thing you should do? Yeah. And so we do have one, it's 2. And of course, since it says find the zeros, we do need to set this equal to 0. Okay, so we got the GCF. What's our next question? Well, before I do that, I would ask if there's a bx term. Because if not, then we're square rooting, which is faster. Okay? Obviously, there's one here, but let's just review that process. We won't, for this unit, the square rooting to solve, it might come up a little, but it's mostly going to be ones where we have factors that we need to do star on. Anyway, so we do have a bx term, so yes, we want to star this. Is it okay to divide this 2 off? I would. That way we don't have to deal with it, right? Okay, so from here, if we say yes, then we have star would be our main option. If we can't star, what do we do? With the bx term, but can't star. Thank you. Okay, and then this one goes the other way. With no bx term, then we're just going to square root. Which is probably the fastest way to solve a quadratic. Let's just get that square root that squared by itself and then square root. Okay. Factors of 30 that add up to 11. Are there some of those? 6 and 5. Remember that the top number goes with x, and then the bottom number is just added or subtracted. After we do what here? What do we need to check for, right? Jaime, are you with me? How about you, Riley?
I was asking about the quadratic. I thought you were doing the quadratic.
I'm using star. What do we need to do here? Before I write this. No, not this example. Seriously, just be patient. But in general. Go ahead.
Well, Blake already said it.
Yeah, reduce. Don't freak out. Okay, and then just set those two factors equal to 0. A lot of the work that we will be doing in this unit will be leaving them like that and seeing what else we can cancel out because of it, okay? But there will be some of finding zeros for denominators because there's an issue there that we need to address. We'll kind of start addressing that today. So we get 2 places where this crosses the x-axis in this one. Okay, did that go completely smoothly for you? Awesome. That means you're probably in a good place with this. Yesterday I introduced our new unit is about rational functions. And the reason why, what is the root of rational? Yeah, I mean, that's funny that we have that word ration, but it's actually ratio, which is a what? You guys remember what a ratio is? It looks like a fraction where we have some expression maybe it's just a number over another one. That's all. Okay? So it looks like a fraction and indistinguishable from a fraction for all practical purposes. Okay? But in this unit, these will both be polynomials. Okay, so you're going to see today's work is not going to look like polynomials because we're starting off with the very, very basics. And then tomorrow we'll jump into polynomials a little bit. But it's poly over poly, right? It's a polynomial rational function. That's what you're looking for. Today, let's start by getting this note packet set up actually. And then today, like I said, just the simple stuff. We're not going to actually define what a rational function is officially until probably tomorrow. Like I said today, getting our feet wet with what's called an inverse variation. Which will lead us to the reciprocal function. Okay. What does inverse mean to you? What was it? Yeah, it's kind of like flip. It's do the opposite, kind of. Okay. We'll come back to this. Just wanted to prep you for what we're about to see. So I'm going to skip that for now. Okay, I want you to just think through this. We're not going to do all this stuff, what it says. So it says the two rectangles shown both have an area of 144 square units. But they are obviously two different shapes, right? Like one's long and skinny and one's less so. So if we have to fix the area at 144, what has to happen if I increase the length to the width? What has to happen to this width? So let's start with this sort of shorter one. If I start increasing this length, what has to happen to the width to keep this at 144 square units? Okay? Yeah, in other words, like let's say I do this times 3, which is 72. What would this have to do? Divide by 3, because if it stays big, it's not going to be 144 units anymore, right? So as one gets bigger, the other one has to get smaller in order to compensate for that. That's what inverse variation means. They're doing opposite things. Like, what else? As you drive more miles, what happens to your gas in your tank?
Yeah.
Goes down. Those are inversely varying as you drive. Okay? So these kind of relationships, they're common, but different than what we've traditionally talked about. Like usually we do what's called direct variation. Like as I hit my gas pedal, what happens to my speed? Yeah, so I burn more gas, meaning I'm going faster typically, right? Like those are directly related. These are inversely related. Okay? As one goes up, the other goes down. That's the idea here. So let's look at this in a table and talk about how you know for sure if this is true. Because it is a specific relationship. It's not just as one goes up, the other goes down. That's the general idea. First of all, note that we see that. X goes up to 12, Y goes down to 1 from 12. So it looks like it's a possibility. Do you agree? Okay. So to check for sure, we need to multiply all of these X and Y's to make sure they all equal the same product. So like, I think that's obvious, but 1 times 12 is 12. 2 times 6 is 12, etc. If these are all the same product, then it is inversely varying. So can you look at that and say yes or no? Okay. Yeah, all of these products will be 12 all the way across. So yes, it is inversely related. Now, let me finish writing that. What if one of these was like 10? It throws it off, right? It's not going to be a consistent inverse relationship. Okay, let's look at another one. Does the table of values represent an inverse variation? based on what I just told you. So one's going up, the x's are going up, y's are going down, but are they specifically inversely related? No, because we have, I'm just going to write product once here, product. Obviously these are not the same, right? All over the place. Okay. So in terms of an equation for that one, we couldn't do it since we don't have a specific inverse relationship. How about this one? We'll push that up a little bit. You might want to use your calculator probably on that one, huh? If you can do it in your... What should I write right here? Yeah, we're looking for their products. Okay? So is it inversely proportional? Inversely related? Okay. So let's start talking about the relationship. We can kind of get the general idea of how these look just by taking one of these tables that actually does work and writing down what we're doing. Do you agree that in this case we're taking x times y and it's always equaling 25.5? Okay? That's essentially the equation that we use. It's getting there for inverse relationships. The only difference is we want this to be something that can represent any case, not specifically 25. So we will write it as k for a constant. X times y is always a constant value in an inverse relationship. So in the first one it was 12, this time it's 25.5, but it's always equaling the same thing when we multiply. That's all that means. Okay? And then we can take that and manipulate that around. If we wanted, we could solve for y. If I want y by itself, what does that give me on the other side? Take this and get y by itself. K over y, or k over x, right? So now that's a graphable thing because we have y by itself, so we're plugging in x values and getting out y values. So now we could make a graph out of that. Okay? So let's kind of think through what that would look like. For something easy, let's do y equals 12 over x. Well, actually let's leave that one. I'm going to start at 1. So what is y if x is 1? It's 12, right? 12 over 1 is 12. Okay, what if x is 2? 3, 5. Let's skip 5. Let's go 4. Sorry. I'm skipping 5.
Good job.
Yeah, we don't need it for sure. 2, you see where this is going? Okay? So start picturing what this would look like on a graph. And you'll start to get the feel for what an inverse relationship or reciprocal function looks like. At 1, I'm clear up here at 12. We're just going to sketch. Okay? At 2, what happened?
It dropped.
Yeah, it dropped in half. And that's for that particular step. At 3, not quite so much drop, right? Just a little bit less. At 4, a little bit less. 6, now let's skip 1. Now we're down here at 2. Okay, what shape do you see coming out of that? Do you see it starting to curve? Okay, and what happens with these, I'll draw this in. Okay. These are very cool graphs, and I showed you what they'll look like yesterday. Let's think about why. I left 0 off for a reason. If I plug x as 0, what is 12 divided by 0? 0. Not 0. Not 12. Because 12 divided by 1 is 12. It's I. It's not. Plug it in your calculator, please.
It's error.
Yeah, so something, in this case, 12 divided by 0. Guys, do you not have calculators? Okay. You need to get one. So 12 divided by 0 is
Error.
undefined. We're going to say it's not.
I got 0.
Are you serious? It actually
Yeah.
says that?
Yeah. See? You're right.
Oh, no, that's bad.
Oh.
12. Anything divided by 0 is undefined, okay? So I'm just going to put whatever up here. And why is that? It's because you're not actually dividing, right? It's like the math is saying, let's say I have $50 and there's how many, whatever of you, let's say there's 15 of you in here. Sorry. Hey, 15 or $50 divided by 15, that's a value, right? Everybody would get some money. But if I say I'm keeping that money, number one, nobody gets any, but number two, did I divide? No. So I can't say I divided by 0 and got the same thing because I didn't actually divide it. Does that make sense? Miss Jackson, share your money. Oh, I don't want to. But then I don't divide it. It's just in my hands. So you can't say divide by 0 and then say, well, it's 0 because that doesn't work. You can't say, well, it's 50 because you didn't divide. Right, I didn't divide. So it's not, it's just undivided or undefined, excuse me. So let's get close to 0. Because at 0, it's undefined. So what that means for us in terms of this graph is that this line can't go across the y-axis. Why not? It doesn't exist there, right? The y-axis is x equals 0 and it doesn't exist there. So put in 0.1. What is 12 divided by 0.1? You'll need your calculator. Okay? So that's a little higher, right? Like we jump down here, we get to 12. Okay, what is 12 divided by 0.00001? Just stick some zeros in there.
12.
12 divided by 0.00.
Did you put 0.00? Oh, that's why.
I didn't say it was 12. The calculator said 12.
I forgot the point.
Okay, what are you getting when you put some zeros in front of that?
big
A big number, right? So the tinier piece, we say divide 12 by a tiny piece. This thing is going to shoot up here and eventually go to infinity. Okay? What's going to, so we know our graph now is coming up like that. Okay, go out to the right. So make x really big. Do 10,000, let's say. 10,000. What is 12 divided by 10,000? Like predict. If you had 10 cookies and you divided them by 12,000 people, how much does each person get? Like a crumb, right? If you take that 10,000 and make it 1,000,000, what is it basically going to be? 0, okay? So this graph, as we go out to the right, is going to approach the x-axis but never touch it, because it's always just going to get teenier and teenier but never actually be 0. So this reciprocal function is going to approach the y and approach the x, but never actually touch them. Same thing over here, just with negative values. Okay, so that's our parent function. You can see it up there in the middle right graph. That is our parent function for this type. Again, it's because as we get closer to dividing by 0, the values shoot huge. As we divide by huge things, the value is almost 0. Okay. Let's go put some of this down. So as one variable increases, the other decreases, but it has to be in a specific way. So we need to use this very important word, proportionally. Which means in the same way. In the same ratio. Say it that way. So if we're getting 2 times bigger, we have to get 2 times less on the other. It has to be proportional. I'm going to put a dot in there so you know that I'm saying multiply. So x times y has to be what? What do we see with the tables? Has to be some constant number, right? We don't know what. It just depends on the scenario. That number is called the constant. Constant of proportionality. Before I write it though, are we good on this? Because when I asked you, you kind of all just got glassy-eyed. Like, you remember 1 times 12, 2 times 6, 3 times 4? It always equaled 12, right? The constant value. Okay. So that rings a bell? Sometimes you'll hear this also as constant of variation. Oops. So just real specifically, it's the constant value that we get from x times y. I want you to put the other 2 varieties on here. So, or this can be x equals k over y, if we just divide by y, or y equals k over x, if we divide by x. All 3 of those come from the same, they're all the same, just a rearrangement of the same concept. Okay, here's the next thing that we talked about. Any questions on that so far? So this is going to be the parent function for our rational functions that we're going to learn about. So this is a pretty important box. In fact, when we're done, I'm going to put some highlighter around it. Called the reciprocal function. What does reciprocal mean to you? Okay, reciprocal, I think fraction or a ratio. Reciprocal means flip that thing over. Okay, so what's the reciprocal of 3/4? 4/3. What's the reciprocal of 1/2? 2. Or 2/1, but it's just 2. Okay, what's the reciprocal of 5? 1/5. Okay, that's what we're talking about here. So the reciprocal function is 1/x. It's basically flipping x over, right? So can we divide by 0? So what can x not be? X will never be 0 in the parent function because it makes this blow up and it doesn't work. So what does that make our graph look like? Start memorizing. What does our graph look like? What did I just show you? Right? It's two pieces, two wings of this. The top one is from high y values down to 0, and the bottom one is the opposite direction. This is just going to be a sketch to remind you, and then we'll write about it a little bit. Make sure it never touches the x or y axis. It just approaches them, like just gets close to them. Closer and closer, I should say. Okay, I do want to write a description for the parent as x goes to infinity. Actually, let's start with 0. So as x goes to 0, what does y do? It goes to positive and negative infinity, right? From the right, it goes to positive. From the left, it goes to negative. As x goes to infinity, what is this approaching? It's actually both. I guess we could just put both on here. So, as x approaches positive and negative infinity, what's y going towards? Yeah, towards 0. Do you remember the name of what we just wrote from last unit? That's the end behavior of this thing, right? We just have this weird break in the middle of it. That's why we have to write it a little bit differently with the 0 there. Okay? What is the domain of this function? And again, this is the parent. As soon as we start moving this thing around, that changes some. But for the parent function, what is the domain? So remember, we read that left to right. Okay? It's negative infinity to infinity, but what about 0? So we have to cut it out, right? So negative infinity up to 0, and then 0 to infinity. In other words, 0 is not in our domain. How about the range? Yeah, it's the same actually. Only this time the 0 references the x-axis, not the y-axis. I think it's probably worth putting a reminder. Kind of helps lend some explanation as to why it's looking like that. Okay. Everybody tracking? Feeling okay so far? Okay. We will add a little bit more to this, but again, this is pretty foundational for this unit to understand that box right there. Every graph that we graph will be some version of this. There will be variety, but it will come back to looking like this in most cases. And this concept comes up a ton. Cannot divide by 0. Okay? All right. Do you need to do a couple more of these? Or are you feeling okay about is it inverse? Give me a thumb if we're ready to move past this. Okay, that's lots of thumbs up. So, all right, we talked about that. Okay, let's do one that looks like this. In an inverse variation, so we are told that it is, right? We don't have to figure it out. We're just told that it is one. So what's our inverse variation relationship? Look at your inverse variation box. What do we know? Because we know it's inverse. Perfect, thank you. X times y equals k, some constant, right? So it says x is 10 when y is 3. Write the equation. Well, what do we need? Like, we know x and y. What else do we need? We need the constant. In this case, what is it? It's just 30. So we need to know k. To know k. So we make x 10 times y 3. So k is 30. Okay. Now, what good did that do us? Look, read the next part. Then find the value of y when x equals negative 6. What good did that do to find k? Go ahead, Liam.
Y equals k over x.
Yeah. So now we know k, and so we can rewrite as just a generic equation. X, y equals 30. Now we can solve for whichever one we don't know. In this next question, it says x is negative 6. So what is y? Negative 5. Okay? So if this is negative 6, then y is negative 5. Okay, so you sometimes have to find the constant first, and then you can find whatever else you want. This is simple. The math behind it, I mean, but the concept can kind of get to you a little if you're not following. So are we good on how that one went? Okay. Give those two a shot. I'll give you like 2 minutes. And you guys, it's okay to put X, Y. I'm just putting the dot so that nobody gets confused on what we're doing between those two letters. Okay, let's just go ahead and do this one up here. So we get, which one is this? X, so 15 y equals 3. How do you solve for y? Yeah. So y is just a fifth. Or you could do 0.2, but a fifth is fine. Okay, before you pack, or at least before you tune out, let's just do a quick concept check. Let's say x, y equals 10. Okay, if x is 2, what does y have to be, obviously? 5. Okay, but let's check the concept. If x goes to 5, what does y have to do?
2.
Okay, so you notice as one went up, the other went down, but in a way that keeps the value the same, which makes that proportional work, right? And there's infinite other ways we could do this. Like if x went to 4, y would have to be 2.5. And so on, right? We don't have to get too far. Now, I will tell you that this beginning section will not really look familiar to the rest of the unit. It's just establishing a baseline, okay? All right, enjoy your day. Have a good night with no homework. Yay.